In activity 5.8, we're focused on solving radical equations, and we're solving them. We've been solving them graphically by just doing y1, y2 point of intersection, or f of x, and then y equals in Desmos, and then finding that point of intersection. Now we want to really focus on how we do this algebraically. So for number 1 and number 2, I just want you guys to graph them and solve them graphically. So in the first one, we have f of x is the square root of x, or square root of d over 3, and that's equal to 2.5. So I have the two functions into, and then I notice that, again, the square root, so it's starting at 0, 0, and it's shooting off to the right, and I know it's an increasing function, so eventually it's going to get to y equals 2.5. It's just going to be a long way away, so I really want to zoom out, or just as I'm sliding over, and I find my answer to be 56.25, and so I know that this answer, you know that d equals 56.25 when our output is 2.5. And we do the same thing for the fifth root of 4x minus 7, and when that's equal to negative 2. And again, since this is the fifth root, we have to be careful how we type it in. And so we have to use the raised to the 1/5 power. And instead of y equals 2.5, this is supposed to be negative 2 now. And so I can just change that. And I go back in to back to home. And now my function is, because it's the fifth root, it looks like a squiggly. So remember, the domain of an odd index is all real numbers. And so it squiggles down, and I can see that the intersection is much closer this time. So negative 6.25 is where this intersects. So we know that the answer for this one is x equals negative 6.25. Okay, and so that's just a review of how we've been solving graphically. And again, we can solve any equation by solving it graphically, by finding the point of intersection. So we want to focus on how we do this algebraically. And so keep in mind that we're just going to use some inverse operations to do these. Right now we have the square root of d, and it's being divided by 3. And so to undo division, we're going to multiply by 3. When we multiply by 3, we get 7.5 equals the square root of d. And to undo the square root, that means we're going to square, is the inverse operation of square root. So we're going to square both sides, and 7.25 squared is what d is going to be, and when we multiply that out, we get 56.25 equals d, which is the same answer we got graphically. Here we have the fifth root, and that's equal to a number. So in order to get rid of the fifth root, getting rid of the fifth root is by raising to the fifth power. So when we raise to the fifth power, we end up with 4x minus 7, and negative 2 to the fifth power is negative 32. And so we now have 4x minus 7 equals negative 32. We add 7, divide by 4. When we add 7, we end up with negative 25, and divide by 4, and we get negative 6.25. In these two cases, we're going to look at something a little bit different. So we're going to solve algebraically first, and then check our work graphically. So we have two square roots, and so we're just going to get rid of the square root right away, because we need to get the x's out from underneath them. And so I am going to just take, I'm going to square square the the expressions, or square the equation. And when I square the equation, now keep in mind this is 2 times the square root of 3x, and so I have to square the 2, and when I square the 3x, or the square root of 3x, I just get 3x, just like we did above. So now I have 2 squared times 3x, so because this is 2 times the, and then I have just 5x minus 7, because squaring undoes the square root. So I have 4 times 3x equals 5x minus 7. 12x equals 5x minus 7. Subtract 5x. Divide by 7. And I have an answer of x equals -1. So we're going to write the deconstruct story here before we solve, just so we know what we're trying to do. So as a recap, we're going to look at 3 is being multiplied, actually -3 is being multiplied by the x, and then we have this addition of 1, and all of that is taking the third root, and then that expression is being multiplied by 2/3, and then finally I'm going to add 1, so my deconstruction, or my solving process, I'm going to start with 9, and then I would subtract 1, and then now I have this 2/3, so divide by 2/3, and then now I'm left with this, so I'm going to raise to the 3rd power. And then I'm going to, since this is a positive 1, I'm going to subtract 1. And then I'm going to divide by -3. And so go ahead and perform those operations and come up with an answer. Okay, so you should come up with x equals -575.6 repeating, or 2/3. So now we want to check our answers graphically. So I'm going to turn off these, and here are our 2 functions. When we check them graphically, we notice that the 2 times the square root of 3x starts at 0, 0, shoots off. The s of x, or the square root of 5x minus 7, that one is starting at 1.4 and shooting off. They're both increasing functions, so they're never going to intersect with each other. So our answer of x equals -1 is not correct. This answer should actually be no solution. Now the reason why this is no solution, it's what we call an extraneous solution, or extraneous root. And it's because we can solve it algebraically, but in fact it's not a solution, because the answer of -1 is not in the domain of this function. If I plug -1 into this function, or to this equation, 3 times -1, there's a problem there. Same thing, and it doesn't have to be in both of them, but 5 times -1 is -5 minus 7. That makes this negative under here, and so we can't have that. And so we have this problem whenever we're working with even indices, or even roots. We don't have to check the solution for this one because it's odd. And since the domain is all real numbers, -573 and 2/3 is definitely in the range. Okay, so to summarize everything, if the radicals have an even index, the solution must be checked to make sure the solution is not extraneous. Now we can check that by looking at the graph to see if there's a point of intersection, or by plugging in the solution and checking to make sure the solution makes sense. If the radicals have an odd index, then solutions do not need to be checked.